Imagine reading a book where every sentence slowly forgets the beginning. No matter how carefully you read, the first page fades as you reach the end. That is exactly what early transformers experienced. And yet today, modern language models can remember tens or even hundreds of thousands of tokens. So what changed? The answer is not more data. It's not more layers. It's not even more attention. It's simple geometry. Transformers do not naturally understand order. They see tokens all at once, as we discussed in this video. Without help, the sentence "the cat chased the dog" looks identical to "the dog chased the cat." Earlier in this series, we solved that problem in this video using positional embeddings. We added a position vector to each token embedding, giving the model a sense of sequence. But that solution came with a hidden limitation. Traditional position embeddings are absolute. Position 1 means position 1, or position 2 means position 2, and the model only learns position up to a fixed maximum length. If you trained on sequences of length 2000, you cannot safely extrapolate to 20,000. The model has no idea what comes after the position it has seen. That is long context problem. Modern models like LLaMA solve this problem by changing how position is represented entirely. Instead of adding position to embeddings, they rotate them. As simple as that. That is called Rotary Positional Embedding, or ROPE. Let's call it ROP. ROP doesn't encode position as a vector that gets added. It encodes position as a rotation in space. Each token embedding lives in a high-dimensional vector space. ROP rotates that vector by an angle that depends on its position in the sequence. The farther the token is in the sequence, the more it rotates. To understand why it matters, we need to focus on attention. Self-attention compares tokens using dot products. That dot product determines how strongly two tokens attend to each other. ROP modifies this dot product so that relative positions are baked directly into the attention computation. Not absolute position, but relative distance. Here is the key idea. If token A is 10 positions before token B, that relationship stays meaningful no matter where the sequence starts. ROP preserves that relationship through rotation. Mathematically, ROP applies the rotation matrix to a query and key vectors. You can see the abstract formula in the screen. Of course, you don't need to understand the formula itself, but to understand the concept, each position I has an associated rotation angle theta I, which that angle increases smoothly with position. The rotation applied in pairs of dimensions using a sine and cosine function, just like sinusoidal embeddings, but embedded directly into the attention. This rotation does something interesting. When the model computes attention using dot products, the result now depends on the relative distance between tokens and not just their content. The model naturally learns patterns like words close together matter more than words far apart, and it learns without ever seeing explicit position IDs. This is why ROP generalizes so well, because it encodes position as a transformation, not a lookup table. The model can extrapolate to much longer sequences that it was trained on. That is how modern LLMs extend context windows from a few thousand tokens to tens of thousands and beyond that. There's another critical benefit. ROP is applied only to queries and keys, not values. That means it affects where the model looks, but not what information it carries. This clean separation makes ROP efficient, stable, and easy to integrate into existing transformer structures. And this is why models like LLaMA or GPT and Mistral use ROP by default. It preserves three things: long-range coherence, relative position awareness, and stable attention scores, all without increasing parameter count. Without ROP, attention degrades as sequences grow longer. With ROP, attention remains sharp, even at extreme length. That is why long context models are possible at all. But there is still a problem. Even if attention understands long sequences, computing attention over thousands of tokens is extremely expensive, and you need to have high resources for those computations. So the question is, how do models generate text efficiently without recomputing the attention from scratch every time? That is where the KV cache comes in. But let's stop for now. It's enough for today. We will discuss KV cache in the next video. So if you have any comments or any questions to ask, don't forget to comment it down below. And if you like the video, don't forget to smash the like button. Until the next video, good morning, good afternoon, good evening. Bye.